Stars aren't just inhabiting our universe. It turns out they're major contributors to it, from hydrogen and helium produced in the Big Bang to all of the heavier elements produced by stars. Two new papers published this month shed light on how the youngest generation of stars will stop contributing those heavy elements to the universe within their lifetime.
This is Trekzone's Talkin' Science.
My name is Julia Chinkargana. I'm a PhD student at Monash University in stellar astrophysics. So I study the chemistry of stars.
Very, very cool. Julia, welcome to the show. Now, as I understand it, stars are pretty important in building up the universe. Essentially, they're giant factories.
Yeah, absolutely. So if we go way back in time, we know that at the time of the Big Bang, we had hydrogen and helium produced, but everything else on the periodic table has been created after the Big Bang in stars, by stars, around stars.
Well, it's a concept to get your head around. These super hot stars spitting out elements from gas through their sheer power and that nuclear fusion that is well known amongst the scientific community. How does it all sort of work? They're created from hydrogen and helium and they come up with all these heavy elements.
Yeah, so it's a really good question. I'll start by specifying that I look at low and intermediate mass stars. So stars like our sun that aren't massive explode as supernovae. So I think it's much more intuitive with massive stars because you can picture supernova explosion, the gas gets spurted over space. But with stars that can't explode as supernovae, they go through a little bit of a different process. So stars like our sun at their lives will puff up into these big puffy giant stars. So you'll have the same size, but their envelope will expand from, say, 1 R of our sun to 200 times the radius that it is now. So they get this really, really low density envelope. And what happens then is that we have these things called stellar winds, and they start to slowly erode the outer layers of the star and chip away at that gas. And over time, they basically chip away at the whole envelope, and that gas is then contributed back to space. So anything that's in the envelope is contributed back to space. Everything that's in the core is locked away. So we're really interested in what kind of chemistry is going on and mixed into that envelope.
Now, the research you were a part of shows that even minuscule changes to the makeup of the star at its birth will fundamentally change what it produces through its lifetime.
We know that for nuclear reactions to occur, we need really high temperatures and really high densities. So that's in the very center of the star. But as I just said, everything that we do back to space has to be in that low density envelope. So we rely on this mixing process to mix created by fusion, by reactions, and mix those products into the envelope. The idea is that we found when you have higher initial metal content in the gas, it's that mixing process so that all the valuable metals and all the things they're really interested in are locked inside that white dwarf remnant, that core, and they're not mixed into the envelopes. They can't be contributed back to space. So the star can still undergo those reactions, but they're locked away and we don't get to see them recycled in the universe.
So if these stars are constantly adding elements to the universe, I guess then it's the next step to say that the universe is always changing and there could be new things, new elements for us to discover.
When you think about what an element actually is, so when we're talking about hydrogen has 1 proton and helium has 2 protons, I'm not sure about new elements, but what we're really interested in astronomy is thinking about, okay, we've got that big periodic table. Where are those elements actually coming from? It's not, that carbon only comes from this type of star and sodium only comes from this type of star. A lot of stars kind of overlap and make different contributions of each element. So there are particular really heavy elements that can only be formed in low and intermediate mass stars like our sun because they have such a long time scale. So they're formed by the slow neutron capture process. There are other elements that can only be created in really explosive events like supernovae. So it's kind of our project is figuring out where those all come from on the periodic table.
Now, your simulations showed that the high level of chemical enrichment caused the stars to act in a very unexpected way. What was that way?
What we already know about high metallicity stars is that they because of how the elements interact in their gas, they're much puffier than a star with a lower metal content. So a low metallicity star is very compact and tight. A high metallicity star is puffier. So because it's more spread out, they have lower temperatures and lower luminosities, so power output. But what was really interesting is the impact of the higher metal content on the mixing processes that go in the center. Our study extended to a much higher metal content that has been published before. So we're looking at up to 10% metals, which doesn't sound like a lot, but the jump from say 8% to 10% is a huge one. And so our really exciting finding was that at such high metal thresholds, that mixing process is completely stopped. So what that means is that generally we'd have a star born with, say, 2% metals, and then over its lifetime it would undergo nuclear reactions, and we would expect that the gas that it contributes is of a higher metal content. So it produces fresh metals. But for our stars with really high initial content, they're not, the gas that they expel at the end is the same amount that they started with. So there's no net production of metals that they're expelling.
Now, one thing that always fascinates me with this, Julia, is just how you come up with this research and make these conclusions. Because it's not a matter of visiting these stars and digging and exploring, as you might say on Earth or something like that. It's looking at radio data and stuff like that, and the wavelengths of light. I'm guessing, am I sort of in the ballpark here?
Yeah, you're right. It's we can't just go visit these places. We can't really experiment with them in laboratories. So it's important to point out that our work, myself and Amanda, is purely theoretical. So we might have an observational astronomer look up at a galaxy and say, "Oh, there's a ton of element X here. I wonder how that got there." And as theoretical astrophysicists, our job is to figure out the story of what happened to get to that much of element X in that galaxy or whichever situation you want. So we use a series of numerical simulations. We have a few differential equations which we know map how the physics works in stars, and then we iterate them and they go on and they map the evolution of the star. It's difficult though, because we can't necessarily check our results because it's not that there's necessarily a right answer. It might be that element X is not just from this type of star, but it's from a few different contributions. So the best way that we have of checking that is that we've got an international field where people all over the world are using codes that are fun. They use the same equations, but they're built differently, and they're built by different teams who have slightly different input physics and mathematics. So the hope is that you'll have 3 teams around the world using completely different codes who haven't necessarily spoken to each other. And then they all get findings that are relatively similar, and you keep iterating and building on that until you can agree. And then the best way after that is to get an observational astronomer to say, yep, I measured this, that's correct, I think this all fits, until 10 years later, then something, revolutionizes it, and you've all got to start from the start. But yeah, it's a process of iterating by different groups.
Well, we should mention Professor Amanda Karakas. She also had a study which was released this month as well. So working together to study these metal-rich stars. What were sort of the differences between her research and yours?
So Amanda, our first paper was about purely the evolution of these stars. So using those differential equations and saying, okay, at the birth of the star, this is where the temperature, density, and pressure is. And then a million years later, this is where the temperature, density, and pressure is. And we basically quantify those variables over the evolution of the star. But to do that, we only need to follow a few basic nuclear reactions. So we follow the energy-producing ones, like hydrogen to helium and helium to carbon, because they produce the energy of the star. Then I can take her output, so the structure of that model, where those variables are at each time step, and I've extended the network to a series of 77 isotope species. So I'm following reactions that don't contribute a huge amount of energy to the star, but are interesting because of their nucleosynthesis purposes. So looking at where these elements come from. So the two papers build on each other. Amanda started the work with the evolution, and then I've extended the network to look specifically at the chemical contributions of the stars.
Eventually, these stars will expand to become red giants before collapsing on themselves as white dwarfs. At that point, they will become a vault with no further contributions to the universe. It's incredible to think that from hydrogen and helium, the most basic of elements, carbon, lead, and all manner of other elements can be produced. My thanks to Julia for beaming in today for this Talk and Science edition.
Thank you.